Welcome to efficiency of separation. So there are two factors that influence how well two components are separated by chromatography. The difference between the elution times of the two peaks and the width of our two peaks. We're going to discuss how we measure the efficiency of a separation. So as a solute moves through the column, it spreads out such that the concentration versus time curve, in other words the detector response versus time, forms a Gaussian shape. And this Gaussian curve has a standard deviation, sigma, and the longer the solute takes to elute from the column, the wider the band becomes, and thus the larger sigma becomes. So there are two common measures of the width of the peak. The first is the width of the peak at half maximum. So if we have our peak here, we're looking at half height, and that width between the trace here and the trace there. That's the first method. The second method is the width of the baseline between two tangents drawn at the steepest part of the peak, so at the inflection points. And so that width is W, and so here we draw a tangent to our curve at this point, and we draw a tangent to our curve there, and then we're looking at the distance from here to there at the baseline. So for a Gaussian peak, the full width at half max, that W1/2, is equal to 2.35 times the standard deviation, sigma, whereas W is equal to 4 times sigma. The width at the baseline is going to be wider than the width halfway up the peak. Now, the resolution of two peaks from each other is given here. So we have the resolution is equal to the change in retention time divided by WAV, which is equal to the change in retention volume divided by WAV, which is equal to 0.589 times the change in retention time divided by the full width at half max AV. Again, where delta TR or delta VR is the separation between our two peaks measured either in units of time or in volume, and this WAV is the average width of our two peaks measured at the baseline in the same units as our delta TR or delta VR. And our W1/2 AV is the average width of the two peaks at half maximum. So two peaks with various resolutions are shown here. Here we have a resolution of 0.5, and you can see that our two peaks are overlapping quite a bit, and when we add those two peaks together, which is what we'd actually see in the chromatogram, we get what looks like a single peak. But as we spread them out, and now we have a resolution of 0.75, now we get to see that there are in fact two separate peaks there, and if we spread them out, so now the distance between them is 4 sigma instead of the 2 sigma or 3 sigma that it was here. Now we have a resolution of 1.0, and now we can start to see that for sure there are two peaks, and in between those two peaks the value is going closer to the baseline, but it's not there yet. And then when we have a resolution of 1.5, which is a separation of 6 sigma, now we have our detector response in between our two peaks going essentially back to the baseline. So the solute band broadens as it travels down the column. So you can see that at the start of the column it's very, very sharp, very narrow, and as we travel down the column it's getting wider, and as we get farther down the column it's even wider. And so in our chromatogram you'll see something like this, where we have a very sharp peak initially, and then a wider peak, and a wider peak, and if we had another peak coming off later, it would be even wider than this one is. So one major source of broadening is from diffusion. Now remember that diffusion is the net transport of solute from high concentration to low concentration that's caused by random motion of our molecules. The diffusion coefficient is a measure of the rate at which molecules move from a region of high concentration to a region of low concentration. Now suppose we have a concentration gradient dc dx across some plane. So we've got some plane here, and across that plane we've got our concentration gradient dc dx. Now the number of molecules crossing each square meter each second is the flux, which we've symbolized with a J. That flux is proportional to the concentration gradient. So flux measured in moles per square meter per second, that's defined to be J. That equals minus d times dc over dx. So it's proportional to our concentration gradient here. Again, d here is our diffusion coefficient, and note that the negative sign there is required because the net flow is from the region of high concentration to the region of low concentration. Now, diffusion is 4 orders of magnitude faster in gases than it is in liquids. And diffusion is faster for smaller molecules than for larger molecules. Now, suppose that we inject the solute onto our column in an infinitely sharp layer with m moles per unit of cross-sectional area of the column. Now, as our band travels down the column, it spreads by diffusion into a Gaussian profile described by this equation, where C is the concentration in moles per cubic meter, T is the time, and X is the distance along the column from the current center of the band. And note that the band center is always at x equals 0. Now the standard deviation of the band is equal to the square root of 2 times d times t. And if a solute has traveled the distance x down the column at a linear flow rate u sub x in meters per second, then the time it has been on the column is equal to t is equal to x divided by u sub x. And that means that the variance of the band, sigma squared, remember that sigma, our standard deviation, is equal to square root of 2 dt, and that means that sigma squared is equal to 2 dt without the square root, which is equal to 2 times d times x over ux. And now we can combine together the 2d over u into h, still multiplied by x, and now we have our variance is equal to h times x, where h is our plate height. Now the plate height is a proportionality constant between the variance and the distance the band has traveled down the column. And that means that h is equal to the variance, sigma squared, divided by the distance down the column the solute has traveled, x. Now the name plate height arises from the theory of distillation, in which separation could be performed in discrete steps that were called plates. Now plate height is also sometimes referred to as the height equivalent to a theoretical plate. The plate height is approximately the length of column that's required for one equilibration of solute between the mobile and the stationary phases. And that means that the smaller the plate height, the narrower the bandwidth. And so the efficiency of a column, which is the ability to separate components, is improved by decreasing that plate height. Now, decreasing the plate height will increase the number of plates on the column for a fixed length of column. Now, different solutes have different diffusion coefficients, and thus they have different plate heights on any given column. In gas chromatography, the plate heights are around 0.1 to 1 millimeter, and in HPLC, or high performance liquid chromatography, the plate heights are closer to 10 microns. In capillary electrophoresis, the plate heights are less than 1 micron. So the efficiency of capillary electrophoresis is going to be better than HPLC, which is going to be better than gas chromatography. For a solute emerging from a column of length L, the number of plates in the entire column is given here, where x is equal to L, sigma is equal to W over 4, and h is equal to the variance, sigma squared, divided by x. So the number of plates in the column N is equal to L over h, which is equal to L times x over sigma squared, which is equal to L squared over sigma squared, which is equal to 16 times L squared over W squared, where W there has units of length and N is dimensionless. And note that if we express L and W in units of time instead of length, then N is still dimensionless. And we can now relate the number of plates on the column to the retention time. The number of plates on the column N is equal to 16 times the retention time squared times W squared, and that gives us then 5.55 times TR squared divided by W 1/2 squared. Now, if we have an asymmetrical peak that's shown here, we can still estimate the number of theoretical plates by drawing a horizontal line across the peak at 1/10 of the maximum height. So we draw a horizontal line across there. And then we can measure the distance from the peak center to the intersection of this line with the peak on either side. So we're measuring distance A here and B there. And then the number of plates is approximately equal to 41.7 times the square of the quantity TR over W.1, the width at that tenth of the way up the peak, divided by A over B plus 1.25, where W.1 is again the width at 1/10 of the maximum height, so W.1 is equal to A plus B. For two closely spaced peaks, the resolution is related to the number of theoretical plates. So the resolution is equal to the square root of n divided by 4 times gamma minus 1, where gamma is the unadjusted relative retention that was discussed in section 22.3. So note that the resolution scales with the square root of the number of theoretical plates, n. And that is, doubling the resolution requires a column that is 4 times as long. Now note that we can also change the resolution between two peaks by changing the unadjusted relative retention. And this is accomplished by changing the stationary phase in gas chromatography, or either the stationary or the mobile phase in HPLC. So that was efficiency of separation.